Another aspect of chemistry that we're often observed in real life is the oxidation of metals. And so it turns out in an oxidation reaction, those two things are tied together, and so we can see them move back and forth. And so oftentimes in a reaction, electrons are gained or lost by metals or metal ions. And so oftentimes a metal will dissolve, or we can have a metal precipitate out of a solution. So what are some examples that we're pretty familiar with? Well, this is in black and white. This is a rusty boat. And so in this case, we can see that there's ion corrosion. We can have, this is tarnished silver. And so in this case, we're creating silver oxides. Another common example is the Lady Liberty, who is copper oxidation, which is what gives her a green look. She was not always green. When she was created, she was copper. And so in this case, these are real life examples of when we would see oxidation in our personal lives. And so corrosion is the transformation of a solid metal into a new metal compound. The metal compound loses electrons to become an ion. So in this case, if we have, this uses bromide, but if you were to add acid to corrode, you could have solid zinc react with bromic acid to create zinc bromide, which would be aqueous in solution, and H2 gas. In this case, the zinc would have dissolved almost completely, and so you would not be able to go backwards. So keep in mind the direction of the arrows. These are not in equilibrium. Another reaction would be iron plus oxygen will eventually go to Fe2O3. This is rust. And so the oxygen in the environment can create these. And so in this case, if we have this reaction, this is going to lose electrons because there is no charge here. So we have a non-charged entity. In this compound, we know that the charge on the iron is going to be 3+. And so this iron, in order to get here, has lost 3 electrons. In this case, I'm going to note that as an E-, which is an electron. And so in this case, the oxygen is going to have gained the electrons to create. So there would have been 2 of these, and we will have 3 O2-. So this will gain electrons. It'll gain 2 electrons in this case. And so this is how we can get oxidation. And so the oxidation is the gaining of electrons. The reduction is a molecule that gains an electron. So in this case, we can have oxidation and we can have reduction. These two things tend to occur together. And so in this case, we often find redox reactions. So these are redox. Where the oxidation and reduction of a metal or a metal ion are coupled together. But in order to determine this, we're going to be able to need to know the oxidation number. And so the oxidation number, or the ON, is effectively how many electrons any given atom has gained or lost in a reaction. And so oftentimes we need to have the ability to calculate the oxidation number for any given sample. So it turns out that there are a variety of rules on how one can calculate this. So for an atom in its elemental form, the oxidation number is always 0. You can think things like solid metals, oxygen gas, or you could think of sodium metal. So there are a variety of these entities. They are in their native states. Okay. For H2, both hydrogens have an oxidation number of 0. So this is somewhat similar to how you would calculate the charge on an atom. There are a variety of rules, and then you solve for the remaining component. For a monatomic atom, the oxidation number is equal to the ionic charge, i.e. for potassium, K+, the oxidation number is +1. And so in this case, if you have K+, the oxidation number is also +1. For nonmetals, they are usually negative. So for oxygen, the oxidation number is usually -2 for both ionic and molecular compounds. However, the oxidation number for hydrogen is usually +1 when bound to a nonmetal. Think things on the right side of the periodic table, and -1 when bound to a metal. For instance, a metal hydride, like sodium hydride. This is a little bit different. The functions of this hydrogen are not the same as if it were in another compound. The oxidation of fluorine is -1 always, where other halogens are mostly always -1 unless combined with oxygen. For instance, Cl2O, some of the oxides, they're a little bit rare, but in that case, that's okay. But the sum of all oxidation numbers in a neutral compound is 0. For polyatomic ions, so this should say for polyatomic ions, the sum of the oxidation number is equal to the charge on the ion. In this case, what we are essentially saying is that we will use all of these rules to determine the overall oxidation number. So let's work on some examples. So we are looking for the oxidation number of sulfur in these compounds. We can see that sulfur is in multiple different compounds. In this case, we want to be able to look at different things. So for H2S, we know that H2 is always going to be, or H is always going to be +1 in this case. So there are 2 of those, and so we know that there are now +2 charges. In order to create a balanced molecule, sulfur is going to have a -2 charge. Okay, so these are the oxidation numbers for these. Now, sulfur 8 is something a little different, but this is the native state of sulfur. And so based on the rules, we know that the oxidation number is going to have to be 0 because it is in the native state. Okay, but what about for sulfur chloride? So now sulfur has been in different relationships. But in this case, we know that the chlorine is going to follow the rules, which are going to be chlorine is -1. There are 2 of those. Therefore, we have a -2. In order for chlorine to be a -2 and this molecule to be neutral, we are now going to need to have a +2 oxidation number. Okay, so now we can see that sulfur has had 3 different oxidation numbers. But what about in sodium sulfate? So we have a couple of different things. So we have a sodium, we have a sulfur, which is one we don't know about, and we have an oxygen. So sodium is always going to be a +1. There are 2 of these. So we have a +2 total. Oxygen is pretty much always going to be a -2. And there are 3 of those. So now we have a total of a -6. So in order to determine the oxidation number on sulfur, in order to make this a neutral molecule, we need the sulfur to have a +4 oxidation number, because +2 + 4 - 6 is going to equal 0. So in this case, the sulfur is going to have a +4. Okay, so we can see that the oxidation numbers, if we are looking for a specific atom, all of the other atoms are assumed to follow the rules. But let's look at a few other examples. So what are the oxidation numbers for the underlined elements? So in platinum chloride, we know that chlorine is going to follow the rules. So Cl is a -1. There are 6 of those. And so in this case, we now have a -6 charge. So the platinum is going to have to be a +6. Okay. What about for this one, which is antimony fluoride? Okay, so the F is going to follow the rules. -1. Fluorine is always, always, always -1. So now we have a -5. So now we know that antimony is going to be +5. Okay. Ooh, now we have a polyatomic ion. So this is MnO4 and there's a minus sign. It's kind of small. But in this case, we know that oxygen, so we have manganese and oxygen. Oxygen is a -2. There are 4 of those. So we know that we have a -8. It's tempting to just assume that this is going to be +8. However, we need to take into account that there's a minus charge here. And so in order to have 1 left over, we're going to have +7, which gives us a -1 overall molecular charge. And so in this case, the oxidation number is +7, okay? Oh, this one looks tricky too. There are a lot more components. So if we have H, arsenic, and oxygen. So for the hydrogen, we're going to have a +1. There are 3 of those. So it will be +3. For oxygen, it's a -2. There are 3 of those as well. And so now we're going to have -6. When we start to look at these, you're starting to see a pattern, right? So +3 -6 is going to give us -3 left over. So the oxidation number has to be +3. Okay. Ooh, titanium dioxide. So we have Ti, which is the one we don't know about. Oxygen is a -2, and there are 2 of those, which gives us a -4. In this case, we will have a +4 charge as the oxidation number. So oxidation numbers follow the rules, and the rules are that any atom in its elemental form, the oxidation number is 0. For H2, both H's have an oxidation number of 0. For a monatomic atom, the oxidation number is equal to the ionic charge. So for potassium, it'll be +1. For nonmetals, they're classically negative. Oxygen is -2 in both. Hydrogen is usually +1 unless bound to a nonmetal and only a nonmetal, such as sodium hydride. The oxidation number of fluorine is -1. Other halogens are mostly -1. But the sum of all oxidation numbers in a neutral compound is going to be 0. For polyatomics, the sum of the oxidation number is equal to the charge.